Well, thanks for the honor of inviting me to this talk series, and it's a pleasure to share this work. Um, I guess I recently finished my PhD at Caltech under the supervision of Chris Umantz, and now I'm a postdoc at the University of Washington, working with all of the quantum folks there, Andrea Coladangelo, Jerry Lee, and Chinmay Nurk. And um, yeah, I'm excited to explain this recent result on quantum computation. And as Atul mentioned, it has this kind of cryptographic application, or rather, potentially, lack thereof, it turns out. So yeah, really, I think it's, like, yes, we resolve this old open problem in circuit complexity, but I think this question is more of like a taster or a vehicle to explore like deeper mysteries about parallelization in quantum circuits, because this is way more mysterious quantumly than classically. Um, and I also ask everyone else on this call to please feel free to interrupt at any point, because the talk is a little bit short, and it's always more fun when there's a lively discussion. So okay, so without further ado, yeah, this is called quantum precomputation, parallelizing cascade circuits, and the Moore-Nilsson conjecture is false. So the Moore-Nilsson conjecture is this old open problem. Okay. And this is joint with Adam, who just started at University of Calgary, and then Charlie Chen, who's an undergrad at UC San Diego, has been doing awesome work for us, and also Bill Helton, who's a professor emeritus, also at UC San Diego. So I want to start just by explaining, recalling parallelization and exploring the difference between parallelization in the quantum world and the classical world. So starting from way back in the day, a guiding question for us will be whether every program can be parallelized. Put a little more formally, suppose you have a Boolean function using computed by a circuit with S many gates. Can that function be implemented by another circuit of depth that's only polylogarithmic in the original number of gates without blowing up the number of gates in the new circuit? So just to be really concrete about things, you could envision a circuit for the AND function, which looks as follows. So here we just have, kind of an iterated version of the AND function. And size 7, so there's 7 gates, but then it also has depth 7. And we can, of course, rewrite this circuit in the following way, into a binary tree architecture, which doesn't have a blow up in the number of gates, but greatly reduces the depth. So this is the sense in which I mean parallelization. Okay, so this this question is mostly like instantiated when S is poly n, and it's been open since really the start of circuit complexity about what the answer is. This is known as the NC versus P problem. And it's really hard and really mysterious. So it's strongly expected, I think is fair to say, the community believes that not every polynomial time program can be parallelized down to log depth. And that, in particular, some efficient algorithms are inherently sequential. And, this is needed by some kinds of cryptography. So there are these things called time lock puzzles, which some on the call may be familiar with, that have applications to a lot of these decentralized topics and blockchain topics. But basically, in order to get consensus or do certain kinds of protocols, decentralized protocols, you need to guarantee that that people delay their computation slightly. And to do that, you want a program that is efficient to run, but also not amenable to parallelization. So if an attacker has many, you know, super many cores on their computer, they still can't race ahead. And it seems like the security of these things, like time-locked puzzles, is independent of standard cryptographic hardness assumptions. There's very recent work kind of further showing that time-locked puzzles are independent of standard crypto hardness assumptions. You know, on the other hand, we can just remark that if NC does equal P, then okay, you know, this is not, no one else I don't think uses this word, but it would be kind of crazy. Like imagine if you could parallelize gradient descent. This is also seemingly an inherently sequential algorithm. You could train a lot faster. You could do a lot of very interesting things with this. So, you know, it's a difficult problem. It's open since 1981. And the best lower bound on any explicit function in not only P, but in NP, the best depth lower bound is only 3 times log n. So not much progress has been made. Okay, so sorry, you may hear the garbage truck outside. I hope it's not too much of a bother. Okay, so classical version is very mysterious, and I want to next illustrate that the quantum version is actually much more mysterious. So even basic ideas in parallelization seem to break down quantumly. Okay, so to do that, I want to take a very toy problem and examine the difference of classical versus quantum. So consider the following scenario. You have 3 functions, f, g0, and g1, just on the hypercube. And let's just suppose they all have some depth t of n. And I want to consider the following algorithm. So these dotted lines are, you know, we're all still in the classical world. These dotted lines represent classical bits going through these functions. So the idea is first you compute f, and then based on the outcome of f, you either compute g0 or g1. That's this half control thing. It's just meant to denote like a generalized control. So at the end, you should get f of x and g sub f of x of y. And so let's compute the depth of this circuit. So the naive depth is, of course, t of n plus t of n, which is 2t of n. But there is actually a faster way to do it, which you may have in mind, which is that you should actually pre-compute both g0 and g1 before f finishes. So you should take the second part of your input y and just make a copy of it, and then in parallel, run f, g0, g1 together, and then once f is completed, simply select which of the outputs of g you should be delivering. And as long as copy and select take constant time, the total depth is improved from, you know, t of n to t of n to just t of n. So this precomputation trick halved the computation time. Okay, now let's consider a quantum analog of this setup. So instead of functions f, g0, and g1, we instead have unitaries u, v0, v1, all requiring t of n depth. And here I've just written, you know, the natural quantum analog of the previous slide. And just to be super clear about what this notation means, I simply mean do one thing when the control qubit is 0 and a different thing when the control qubit is 1. Okay. So again, the naive depth is 2 times t of n. Okay, but now there seems to be a problem. Can we parallelize this? It seems like not. it seems like there is an obstruction coming from no cloning. In particular, there's no way to copy the state y. So as long as ket x and ket y are both, general states, they're not meant to be necessarily a computational basis state. Yeah, really unclear how to parallelize this, if at all. So this
Could you
suggests,
could you do
yeah,
some crazy
please.
thing, like, I don't know, like have some EPR pairs and you like compute on one part of the EPR and then I don't know, transfer like some teleportation style thing? Because at the end of it, you need only one answer, right? Like you don't need answer to both.
Um,
I don't know if
yeah.
it makes
So
sense. I'm just
yeah,
speculating
yeah,
here.
yeah. So one can absolutely play around with this kind of thing, and maybe one thing to your point, Atul, like you could maybe guess that the correct unitary to apply is V naught. Um, but then, well, yeah, essentially, yeah, yeah, you can try these teleportation tricks and try things like this. Unfortunately, none of this works.
I see.
And uh, okay, maybe it does, but I think the idea would have to be far outside of like typical approaches.
Yeah, I don't know. I see what you're saying. Because are you
Yeah.
familiar with there was this paper by I forget by Henry Yan and others,
Mhm.
I think, which was looking at randomized encodings. I think I may have even mentioned it to you when I was back
Uh-huh.
there. We're doing something
Uh-huh.
very similar. They were saying like there's a giant circuit, and then you can do like this teleportation like thingy, and then you can compress it and
Uh-huh.
create a stack coding. So I wonder if there was any connection, but I guess from what you're saying, there isn't any obvious connection. Yeah.
Yeah, and I mean I can only tell you like my moral takeaways of this problem, which is that really um, it seems unavoidable to do because we're doing a full unitary. It seems unavoidable that to parallelize this, you need to clone y. Like you
I see.
can't
Okay.
um, somehow like you can't teleport and not teleport at the same time.
Mm.
Or if you tried, you would have to rewind the branch that you didn't want to compute in the end.
Mm.
And that
So that had
rewinding
to be
takes
done.
just as
Yeah.
much time.
Right.
Exactly right.
Okay. Thanks.
Exactly right. So, yeah, of course, thank you for the question. Okay, so this is the setup. I don't know, to me it's like pretty compelling and exciting because it suggests in much more broadly, I would be really excited if there's an easier way to prove a separation between the quantum version, quantum input NC, so like, unitary QNC from BQP, unitary BQP. I would it'd be really, really exciting and compelling that this might be easier than the classical version. Okay, so this toy example kind of leads into what is one intuition for the conjecture made by Christopher Moore and Martin Nilsson back in 1998 when they posted this preprint on the archive where I mean this is the paper that defined QNC0. So this is really the originating work in quantum circuit complexity. They said, hey, how about this circuit, which looks just like an iterated version of what we were just talking about? Certainly, this thing requires linear depth. And the conjecture is that as long as all of these unitaries are neither diagonal or anti-diagonal, so yeah, zeros in the on the diagonal, um, as long as all these unitaries are neither one of those, then this thing should require omega of n depth. And, it's really compelling because if you think about what kind of classical circuits look like this, you could imagine C naughts, like classical reversible computation. And so that in particular, that's the anti-diagonal picture. And all of the classical things can be parallelized. There's very, very old techniques for parallelizing C naught networks, stuff like this. Um, but it seems like the non-commutativity, the quantumness of this unitary circuit kind of, yeah, blocks all of those ideas. And It's an very appealing candidate for getting inherently sequential computation. It would mean that even simple quantum circuits cannot be parallelized, and large coherence times are necessary for even simple things. And as Atul mentioned, it could also lead to schemes for verifying device depth. So the idea is that maybe there's a family of states that can be produced in constant time, yet to do some unlocking type procedure on this family of states, you need to run one of the circuits pictured here, which would take a much longer time. So there's and that's really like a unitary time lock puzzle type of like in spirit there. Okay, so and this was sort of posed in 1998, and yeah, as far as we know, there was no published progress on this conjecture since then. Through personal communication, several people have come across this circuit or related circuits, both in cryptography, but also in measurement-based quantum computing. There's circuits of this form that appear there kind of naturally. And yeah, so I think there's a lot of belief that it should require linear lower bound, but in fact it does not. So anyway, actually, before I just explain the results, let me take a step back and just say the Moore-Nilsson conjecture highlights like two big motivations for studying quantum parallelization. So the first is that wow, our ability to parallelize quantum circuits is very far behind our ability to parallelize classical circuits. So we're far from even being able to recover quantum versions of classical parallelization ideas or prove that they're impossible. So I think it's kind of funny that such a simple circuit took so long to resolve, and especially as we move towards this intermediate scale quantum computation, error correction is starting to look pretty good. It becomes more and more meaningful to understand how to parallelize things and fit them on near-term devices. Yeah, and the other thing is, maybe it's hard because it's different. So maybe it's easier to prove that there exists inherently sequential transformation. Okay, so as I alluded to in this talk, we'll explain how these unitaries actually can be parallelized down to log depth. So the theorem is exactly as you'd expect. Maybe some highlights is that the parallelization is exact, and it also requires no ancilla. So this is a bit surprising. And as a bonus, okay, well, so the parallelization, we'll see, it uses like all-to-all connected circuits. And you could ask, okay, well, what if I have a geometrically local circuit? So sort of as an example, if you have 2D circuits, you can get square root n depth. Okay, you have to pay a little with ancilla, but you can parallelize it down to square root n. And, just the remark that in both of these geometric regimes, these are the best possible upper bounds there's a matching light cone lower bound. So, okay. And then more generally, we also proved depth reductions for what one can call controlled cascade circuits, which are slight generalizations of Moore-Nilsson. So if in this picture above, all the unitaries were actually acting on more qubits, so that's still one qubit of control down to the next unitary, but UK acts on, let's say, log n qubits, then this has also a parallelization of depth down to n log n using some ancilla. And we can compare this to the naive depth of n squared. Why is this the naive depth? Well, each unitary is on log n qubits, so naively requires depth polynomial in n, and that times the n many unitaries gives you naive depth of n squared. Okay. Any questions at this point? Great. So it's actually easier to explain things starting from this more general but weaker framework, and then specializing to the Moore-Nilsson circuits. And it's really about how could we recover some of these precomputation ideas from the toy example at the beginning. So let's consider the simple case. Okay, M in this picture will be 3 in general, M can be any integer, but for these pictures, M will be 3. So consider a cascade of this kind. How could we parallelize this circuit further? Well, let's just note that ancillary circuits for general k-qubit unitaries have worst case depth 4 to the k over k. We're going to forget the denominator for the purposes of this talk, but so roughly 4 to the k. And if we use this fact, then this depth naively is m times 4 to the k. But let's just observe that if these v's were diagonal, then it would be much cheaper to do this. So ancillary circuits for diagonal k-qubit unitaries have worst case depth a square root of the general one.
Joe,
Okay.
sorry, I have a very, very stupid question. So,
Uh-huh.
when you're stating this fact, the unitary is given as a, I guess, 2 to the k cross 2 to the k matrix, and we're asking if there's like some gate decomposition for which it's
Yeah.
small. It's the gate decomposition given, and you're given a giant circuit, and you're asking whether it can be compressed. What I mean to ask is whether it depends on the choice of the gates, or somehow,
Oh,
or
yeah. So if we assume a model which is arbitrary 2-qubit unitaries
Mhm.
and it's ancilla free, then there are explicit lower bounds on the depth.
approximate? Like, does it have to approximate the unitary, or is it exactly the same unitary?
Oh, this is
If you have gates,
exact. But I think that as long as you care about like operator norm approximations,
it
you know,
would
like
go. Okay.
it's kind of smooth in that way. Yeah. Maybe side comment is that if you only care about L2, like if you only care about average case approximations, you can do much better in some cases.
Nice.
Maybe we can talk about that at the very end. But yeah, so I don't know the answer for, I mean, these are really just counting arguments. And yeah, so even in the approximate thing, you can take an epsilon net and it all ends up being roughly the same. So, okay. So the idea is maybe one line of attack is, can we somehow make these VIs diagonal and just get some savings that way? So to start walking down that road, here is a first attempt. So here's our circuit, and we know that this is expensive, but we want to try to turn the VIs diagonal. So let's just simply diagonalize them. So here I've written VI as UI, DI, UI, dagger. And you'll notice the UIs do not have controls on them. That's fine, because if the original controls were 0, then the UIs just annihilate each other. So this is fine. Okay. And we can pull the U's to the left. So here we're witnessing our first little bit of parallelization. We're only paying 4 to the k, even though there are m many unitaries being computed in simultaneously. So this is some notion of precomputation. Also, things are looking good because so D always will denote a diagonal circuit. Things are looking pretty good because now we're only paying m times 2 to the k depth here. Okay, but so that's an improvement. But of course, we still have an issue with these guys at the end. It doesn't seem like you can pull these UIs, the UI daggers, out to the right because they don't commute with these controls, which is no fun at all. Okay, so what can we do? Well, we need a better identity than simple diagonalization. So here's a lemma. For any many qubit unitary U0, U1 of this form, you can rewrite it. Okay, this looks way more complicated than simple diagonalization. Maybe we can just stare at the difference. What we've done, so we've given something up and we've gotten something in return. What we've given up is that the unitary after the diagonal one is now it's connected. This R is controlled by the top level qubit. But in return, this R is controlled in the last qubit in the computational basis. If you recall, the problem on the previous slide is somewhat ameliorated now, given that these things are all on the computational basis. We also have appearing is a 1-qubit unitary phi, which it's just a fixed unitary. It won't really end up being a problem. So we have this identity. Let's see how it can get applied. Okay, so back to where we were.
Which
We're
is
gonna,
true.
yeah.
Was that number you guys came up with it?
This is this is like one of the key ideas in the paper yeah. So I mean, we'll see a proof of it later. It's not it's not too many steps away from kind of basic ideas in linear algebra, but yeah, this was like one of the first realizations in this project.
And just to be sure, so when you say phi is universal, you mean it doesn't depend on the U0, U1, whatever. That's basically.
It doesn't depend on U0.
U1.
Yes, that's right. That's right. Phi is literally like square root of the Hadamard matrix or something. So
got it. Thanks.
Yeah. Of course. Okay. So let's apply this identity. Here I've inserted it for each of the unitaries, just making the middle one blue for visual clarity. And as before, we can pull all these p's over to the left. And what's new is that because these ri's, they are controlled at the top and bottom qubits in the computational basis, it means they commute with the other things to their right. So we can do this. Let me go back once. Okay, so the p's go to the left, r's go to the right. Okay. And now, so let's count our depth here. So the original depth was m times 4 to the k. In the new circuit, well, we have this one column, which is going to be 4 to the k. Now we're only paying m times 2 to the k for these diagonal plus 1-qubit gates, which don't really factor in anything. And then these r's, no matter how deep the circuit will be, there'll only ever be 2 columns of r's because they all commute with each other. You can alternate left-right column. So the new depth is as written. Okay. And as a concrete example, if you instantiate this with m equals n and k equals log n, then we get polynomial savings in depth from n cubed to n squared. Okay. The other thing to mention, I'll just flash the slide here is that if you allow ancilla, you can get even better savings. So, okay, it's kind of chaotic looking, but there's kind of classical tricks in phase kickback to further pre-compute. This cascade of diagonals, it's almost classical, because diagonal unitaries are almost classical computation. So you can parallelize those further with some old tricks and get further savings. So here we went from m times 4 to the k to 2 to the k over 2 plus mk. And that gives us, in particular, the example corollary from the results slide. So yeah, depending on your taste, this bean counting is maybe not so interesting, but maybe has some practical use.
So maybe just trying to understand the first trick that allows you to have these diagonal matrices, because it seems that once you have these diagonal matrices, then you can sort of commute and have this more compact description.
Yeah.
But I'm trying to gain a bit more intuition on how you introduce this diagonal, because it wasn't just a diagonalization of those unitaries. So I'm trying to gain a bit more intuition about the first trick. Where does this come from? If you could say a tiny bit more.
Yeah, okay. I can maybe give you the intuition for why one might think about pursuing an identity of this form. And then after that, we'll actually proceed directly to the proof of this lemma. So that might also be answering your question. Good. So here, I guess the narrative may be more clear in hindsight than when we were trying to solve the problem, is that if you do naive diagonalization, you get stuck precisely because the UI daggers, so the diagonalizing unitaries on the right, can't commute past these diagonal gates. And so really all you want is for the UI daggers to be somehow decomposed where they're controlled on the bottom qubit.
No, I see. So that's why I introduced this phi and the control on. Okay, I see.
Yeah, so we went from the U daggers to this R, and it's kind of miraculous that the bottom qubit controls it in the standard basis. In return, we allow it to be controlled by the top qubit, but that ends up not being too big of a deal.
I see. Okay, thank you so much.
Yeah, we kind of like realized that we wanted an identity of this kind, but then it took much longer to understand that actually it's possible for any unitary. Like we thought it shouldn't be true for any unitary, but then then things ended up being as they were. So okay,
Very nice.
so thanks. Yeah, so anyway, we get these results. So let's see, where the heck does this identity come from? Okay, so we're starting with the unitary next to the equal sign, and our goal is in this cloud, so we can keep our goal in mind. And one trick that we'll use several times in this talk is to ask for forgiveness rather than permission. So let's pretend that the first qubit is in fact ket 0. And then if it was ket 1 instead, we'll just rewind. Okay, this allows us to simplify the control of the first qubit down to only doing something when the qubit is 1. And we can pretend these two, U dagger, U naught dagger, U1 is like one unitary. And to this unitary, we're going to apply a classical fact from linear algebra called the cosine-sine decomposition. So written as a circuit identity, it looks as follows. It is more recognizable as a theorem. So, okay, this is true not only for unitaries, but the unitary instantiation says, if I cut my unitary up into square blocks, 2 by 2 blocks, then there's it can be blockwise diagonalized into these singular value matrices. So sigma 1 is the singular values of U11 and U22, and sigma 2 is the singular values of U12 and U21. And if we look at the circuit that is written here, we see that these control S and control T guys are really exactly implementing the block diagonal pieces here. And this maybe takes a little bit longer to think about, but it turns out that a diagonal conjugated by a certain 1 qubit unitary just on the last qubit is going to give you exactly something that looks like block diagonal. So this really is a circuit expression for this fact. One thing that maybe is slightly confusing is that we've interpreted this fact as a circuit, and then we've applied that circuit actually upside down. So if you want to exactly match like the typical way that the tensor product is written, really you want the phi's to be at the top and the controls to be on the top qubit. This is why you would get a block diagonal matrix. Okay. So anyway, cosine-sine decomposition, it has reappeared many times in quantum computing. Also, recently has been a nice way to think about QSVT, for example. There's this nice paper by Ewan and a colleague on that. Okay, so now we've rewritten things with this cosine-sine decomposition, and we're nearly done. Recall our goal in the cloud. Again, we're going to ask for forgiveness rather than permission. So replace control S on the top with uncontrolled S dagger. Once we've done that, actually, with a little thought, you realize that this commutes all the way through to the right. And the reason for that is it actually, we're only applying S dagger ever if the first qubit is 0. So it doesn't even talk to kind of the rest of the circuit. So we can commute it over. And then we just group these unitaries and give them names, and we're left with our final result. Okay, great. So we have completed this kind of general framework for thinking about parallelizing these sorts of circuits. I'll now move on to talking about the what's kind of special about Moore and Nilsson and why you get exponential depth improvement. So maybe I'll just pause one more time for questions. But yeah, it sounds like things are going well. So okay, so how the heck do you get exponential depth improvements in the case of these in the case that the UIs are 1 qubit? So the general idea is to apply the framework from before, but before applying it, to group the controlled unitaries, remember now they're 1 qubit, into big chunks, into blocks. So our new VIs, we should always think of them as having a tiny little Moore Nilsson cascade inside of it. Okay. And it turns out that when you examine the precomputation identity that we just proved for these blocks, for these little cascade blocks, you get something much nicer. So compare this new lemma, which is improved precomputation for Moore Nilsson circuits, compare it to the general case where it's general U0 and U1. So the main thing is that the middle part, this diagonal part, it now only interacts with the first and the last qubit. And okay, so Q is not actually diagonal. What I've done is I've kind of pulled a phi out of P, and I've multiplied both sides of a 1 qubit diagonal matrix by phi. It's, up to kind of trivial modifications. These are directly comparable. And really the point is that the diagonal is now only on 1 qubit. Then we're skipping all the intermediate qubits. Okay, so why is this so valuable? Well, let's apply this precomputation identity and see what we get. So here we start. Remember, these are blocks of little pieces of the cascade circuit. And with this identity, let's plug it in. As before, we can pull things to the left and to the right. Okay, but now what? What are we left with? So we see we have another cascade, and there's 1 qubit. It's a cascade of 1 qubit unitaries, controlled unitaries, and they skip all of these middle qubits. So in particular, they're another Moore Nilsson circuit on many fewer qubits. So the idea is to recurse. So we can kind of clean up and finish up by doing the following. Let Mn of little n be the minimum depth of a Moore Nilsson circuit. Then it's at most 4 to the k plus the same, but on many fewer qubits. So n over k. Remember, k was how many qubits are in each chunk from before. Remember when we grouped things up? But now we have a circuit only on n over k qubits. And after L iterations, we get this. So simply setting L to be theta of log n and k to be a constant, we end up with log depth in total. Okay. So that's like how this identity gets proved. I have some slides explaining why the identity is true. So the point is that there's actually a special structure for the relevant cosine sine decomposition. So if you recall, we applied in the general framework, we applied the cosine sine decomposition to, we'd asked for forgiveness, and we had this controlled V0 dagger V1, and we applied the cosine sine decomposition to that. In the case of Moore Nilsson, and when we instantiate V0 dagger V1, it looks like this following pyramid type of circuit. And here, under the hood, the key thing we gain is that this cosine sine decomposition also is much nicer. And right, okay, so here's the comparison. And so I'd like to explain why this is true. I think this is kind of the algebraic surprise that enabled the parallelization of Moore and Nilsson circuits. So it's easiest to think about this where everything is upside down. And what we're going to explain why this identity could be true, we're going to actually analyze the version where we flip the order of the qubits. So the claim actually is that this thing on the left, written as a matrix, looks like, and I'll explain what this blockwise similarity is in just a second. It looks like a matrix that has, it's some mysterious thing in the top left and bottom right blocks, but then it is fully anti-diagonal on the top right and lower left blocks. So what is this notation? I mean exactly similar in the sense of the cosine sine decomposition. So we say A and B are blockwise similar if there is a way to get from A to B by conjugating by these block unitaries, okay? And it turns out that this main claim is enough to finish the theorem. So before proving the claim, I'll say why it gets you the thing on the right. Okay, so say we had this. Well, what we can do first is we can apply a permutation on the right, and this permutation is blockwise to make those anti-diagonals diagonals. And then we can diagonalize the gray boxes, essentially do an SVD to get them also on the diagonal. And then it turns out that by unitarity, you get that these unknown diagonal parts all have the same, without loss of generality, are actually all the same. So they have the same magnitude, and then you can apply a diagonal unitary to make them all literally the same. So we're left with a picture like this, and we can actually factor this matrix. It's exactly a 1-qubit matrix times the identity. So it suffices from the point of view of blockwise similarity, it suffices to show that the explicit matrix defined by the circuit on the top left is similar to this picture here. Okay. Right. Okay. Yeah, I guess. Yeah, so this Q, you can see exactly where the Q times identity plugs in our target. Okay, so why the heck does the circuit look like this or similar to this in any way? It's actually, how we discovered this was really just through numerical exploration. You look at the circuit and you notice that it's sparse in the upper right and lower left-hand columns. And that sparsity can take you almost all the way there on its own. And I'm going to really quickly prove why it's anti-diagonal. So let's first examine what's going on in one of these blocks that are off diagonal. So if you let M be the circuit, this square that I've just highlighted is exactly a point where on the left-hand side, the row we're choosing starts with a 0, the column we're choosing starts with a y, sorry, it starts with a 1, and then the rest of the coordinates, x and y, we're promised that there's at least one where xi equals yi. This is how we ensure we're not totally on the anti-diagonal. So this is like the general form of one of these off anti-diagonal boxes here, okay? And just a proof by example, here's a particular instantiation, choice of bras and kets, matching this pattern. You'll notice the first bra and ket are 0 and 1, and then there's at least one coordinate, in this case, the third qubit, where the bra and the ket are equal to each other. So if we look at what this does to this valley type of circuit, well, we know that U3 dagger and U3 will both be applied because the bra and the ket are equal to each other. If they were both equal to 0, neither U3 nor U3 dagger would be applied. In either case, these unitaries, an equivalent circuit is this. So these unitaries annihilate each other. And once you have anywhere on this valley two kind of partner unitaries disappearing, everything above cancels out, so like annihilates. You can just bring them together and they disappear. And in particular, the first qubit, which is guaranteed to have a bra 0 on the left and a ket 1 on the right, looks, these are orthogonal, so it's always going to be a 0. Okay? And then a somewhat similar argument allows you to analyze the top part. So the main difference is that this full antidiagonal has all of the coordinates of x not equal to the coordinates of y. And here's an example of that situation. What this means is that for each controlled unitary, like ui, either the dagger version will remain or the non-diagonal version, or the non-dagger version will remain. So in this example, I've just removed the unitaries, the controlled unitaries that aren't applied. And what we see is that this inner product is a constant depending on x and y. And in particular, very, very crucially, the modulus of this complex number, the absolute value of this constant, is independent of x and y. And you might wonder, well, why is that? Well, it's because we're always guaranteed that one of that like either the bra will be 0 and the ket will be 1, or vice versa. That means that c sub x comma y is the product of the entries on the off diagonal of these 2-qubit unitaries. And only for 2-qubit unitaries are we guaranteed the following fact: the modulus of the upper right and lower left entries are equal. So very, very conveniently, all of the numbers in this gray antidiagonal, they might be different complex numbers, but they have the same modulus. And that is what allows us to multiply, let's say, for example, right multiply by a diagonal to get from these, unknown numbers of equal modulus to what's pictured here on the right, which is meant to represent literally the same number. Literally the same complex number.
So is that why, Joe, it was the case that you were saying that if you increase the field or something, then things like instead of qubits, if you start taking qubits or something, then is this where
Yeah. This is one of the we'll get to that at the very end. This is absolutely one of the reasons why things break down. Yeah, there's like also a kind of a worse reason that things break down, but this is definitely one of them. So
I see. And numerically, do you see that something like this happens? It's just that we don't know how to prove it, or numerically you already start seeing off diagonal, whatever, like not anti-diagonal.
Good question. I don't remember. I don't remember. Yeah, yeah, it's a question for Charlie. I think there might be much more chaos appearing in larger circuits. Yeah. It's a great question.
Cool. Thanks.
Oh, thanks. Yeah. So, okay. So I've shown you how the sausage was made. I've shown you how the sausage was eaten, and we've now proved the Moore-Nilsson conjecture is not true, in my opinion, sadly not true. Okay, and what's next is I just want to highlight some like future things. So taking stock of what we've done, we found some techniques for parallelizing of this very particular kinds of circuits, and we resolved the Moore-Nilsson conjecture. However, what about the epsilon neighborhood of the Moore-Nilsson conjecture, right? There's like, I mean, Atul already brought up, what if you do this for qubits? So it turns out there is so much unknown. Like you can push these techniques a bit, and we've been doing that since this result came out a little bit, but really I have no idea. We have no idea what to say about a lot of ways you could imagine modifying the Moore and Nilsson conjecture. So let me list a couple of them. One of them is if you have more than one qubit of control. So if you have, let's say, target unitaries on more than one qubit, or even on qubits, let's say, completely, and then you allow, this larger, subspace, or Hilbert space, to tensor product space to control the next unitary. Really don't know how to do any parallelization at all, like not even the general framework. But I don't know how to gain depth at all. Relatedly, what if we don't have controlled unitaries? What if they're just arbitrary 2-qubit gates? No idea. Absolutely no idea how to save in depth here. Yeah, and I mean, in particular, all of the techniques we saw in this talk relied on being able to commute things past each other and kind of restrict to the case where things share the same basis, like computational basis, for example. Unclear how to do that for general even just 2-qubit unitaries. Okay, and then thinking maybe a little more creatively, in some sense, this Moore-Nilsson thing looks like one-dimensional quantum programming, or a one-dimensional memo table, in the sense that you have, your ith qubit depends on the data stored in the I-1th qubit. And, in general, classical dynamic programming, you want more than just one-dimensional tables. You want 2D or higher dimensional tables. And there are some techniques for parallelizing general dynamic programming in the classical world. Can you do the same quantumly? So in this right-hand picture, I've drawn like one example you might imagine as like a fully quantum version of dynamic programming, and we have no idea, even when the targets are 1-qubit, we have no idea how to parallelize this when both the x and y coordinates are growing with n. The number of cells in x and y are growing with n. Yeah. And then question for anyone on the talk and anyone who might be watching this video later. I'm always interested to hear more examples of circuits that should be parallelized, especially for applications. It's good to have, it's good to have a specific target in mind. Yeah, and maybe I'll finish just by explaining kind of concretely what breaks down if you try to do this qubit thing. So here on the left-hand side is the cosine sine decomposition that's true. If you repeat things, if you just try to do everything for qubits, you end up needing a cosine sine decomposition for 3x3 block matrix instead of 2x2 block matrix. And one thing to appreciate is that in the 2x2 case, we have these 4 unitary blocks, U11, Uij in general, and then we also have 4 unitaries on the diagonal. We have S1, S2, T1, T2. So in some sense, there's just as many little unitaries that we want to diagonalize as there are diagonalizing unitaries. This is good because, like, from a parameter counting standpoint, at least we have the sufficient condition that there's as many degrees of freedom as there are things we'd like to control. Once we move to 3x3, this is no longer the case. We have 9 submatrices we want to simultaneously diagonalize, but only 6 kind of tools for doing that diagonalization. And in particular, it cannot be done in general. So there's already a counterexample at 6x6, and so not even 2 qubits. That's like 1 qubit and 1 qubit. And in particular, like any unitary that's proportional to 1 with an upper left rectangular block looking like this cannot be simultaneously tridiagonalized. So yeah, one kind of general point is the techniques explained in this talk are very algebraic. So they're very rigid. And what I would love to see is a softer approach to diagonalization, one that is like more about approximation or randomness, because that, in my mind, that has like some more hope to be more general, but I think even like any approach like that will also somehow have to contend with the intricacies of the algebra and these tensor product spaces. So with that, I will conclude. Thanks so much for your questions and attention.